Ever pondered about what could happen if you traveled at the speed of light? The very thought teems with exhilaration, doesn't it? The concept of light-speed travel has always held an irresistible allure, a tantalizing enigma that has captivated minds for generations. This video embarks on a journey to delve into this intriguing concept, to explore the boundaries of what we know and what might be. So are you ready to unravel the mystery? Let's dive into the enigma of light-speed travel. Albert Einstein, a name synonymous with genius, revolutionized our understanding of time and space. This man, with his iconic wild hair and thoughtful gaze, shattered the long-held Newtonian principles of mass, motion, and gravity, and replaced them with a new way of looking at the universe. This new perspective is what we now know as Einstein's theory of relativity. Einstein's theory was a game changer. It proposed something radical, that mass and energy are interchangeable. This was the birth of the mass-energy equivalence concept, summed up in the famous equation E = mc squared. Here, E represents energy, m stands for mass, and c squared is the square of the speed of light. This equation tells us that even a small amount of mass can be converted into a large amount of energy, and vice versa. But Einstein didn't stop there. He also suggested that there's no absolute frame of reference in the universe. Everything, including time, is relative. What does this mean? Well, imagine you're on a train and you decide to throw a ball straight up in the air. To you, the ball seems to go straight up and then straight down. But to someone standing on the platform, the ball appears to follow a curved path. Neither of you is wrong. You're just observing the event from different perspectives. This relativity also extends to the speed of light. Contrary to what you might think, if you were to race alongside a beam of light at half its speed, the light would still zoom past you at its full speed. The speed of light remains constant, regardless of the observer's state of motion. So why does all this matter? Because it forms the basis for our understanding of the universe. It helps us comprehend why we can't travel at the speed of light, how gravity works, and why time isn't as straightforward as we might think. Einstein showed us that the speed of light is a universal constant, and that's where things get interesting. The speed of light, an astounding 299,792 kilometers per second. But what happens when we try to match this speed? The universe has set some ground rules, and one of them is the speed limit, which is the speed of light. This cosmic speed limit has profound implications for everything from our understanding of physics to the nature of time itself. Now imagine for a moment that you're an object trying to reach this speed. As you accelerate, something peculiar happens. Your mass begins to increase, not just by a little, but exponentially. This is a consequence of the relationship between energy, mass, and speed, as proposed by Einstein's theory of relativity. You see, as an object moves faster, it gains kinetic energy. But this energy doesn't just disappear. Instead, it gets converted into mass. This means that the faster you go, the heavier you become. And as you get heavier, it takes more energy to keep accelerating. This creates a sort of cosmic feedback loop. The faster you go, the more energy you need to keep going faster, which makes you heavier, which means you need even more energy, and so on. When you reach the speed of light, your mass would become infinite. And to move an object with infinite mass, you would need an infinite amount of energy. This is a paradox, and it's one of the reasons why nothing can travel at the speed of light or faster. So, attempting to match the speed of light is like trying to reach the end of a rainbow. The faster you go, the further away it seems. It's a goal that's always just out of reach, no matter how hard you try. The universe, it seems, has a sense of humor. It tempts us with the possibility of light-speed travel, only to snatch it away with the reality of physics. So, traveling at the speed of light is off the table, but what about nearly as fast? Imagine moving so fast that time itself starts to slow down for you. Yes, you've heard it right. This isn't a plot from a science fiction movie, but a fascinating consequence of Einstein's theory of relativity, known as time dilation. Time dilation is a difference in the elapsed time as measured by two observers due to a relative velocity between them, or to a difference in gravitational potential between their locations. When an object approaches the speed of light, this effect becomes significant, and time can appear to slow down. Let's delve a bit deeper into this. According to the theory of relativity, time is not an absolute quantity, but is relative to the observer's speed and gravitational potential. The faster one travels, the slower time appears to pass. This isn't something we notice in our day-to-day lives, but at speeds near the speed of light, the effect would be dramatic. Now, let's imagine you're traveling at 90% of the speed of light. To you, inside your spaceship, time would seem perfectly normal. Your watch would tick away as it always does. Your coffee would brew in the usual time. But to an observer back on Earth, your time would appear to be moving significantly slower. This is because as you move closer to the speed of light, time dilates or stretches out. The seconds on your watch would take longer to tick away compared to the seconds on an observer's watch back on Earth. It's almost as if you're moving through a viscous time, where every moment is drawn out. But remember, this isn't because your watch is malfunctioning or because there's something wrong with you. It's a fundamental aspect of how our universe works. So if you were traveling at 90% the speed of light, you'd be in for a time-bending experience. You'd be living proof of one of the most incredible predictions of Einstein's theory of relativity, demonstrating that time isn't a fixed, unchanging entity, but something that can be stretched and squeezed by motion. Let's take a hypothetical trip to Mars and back at 90% the speed of light. Picture this. You're in a spacecraft, blasting off from Earth, destined for Mars. The engines hum and vibrate as you accelerate, pushing you to speeds that are 90% of light's blistering pace. As you zip through the cosmos at this incredible speed, you're not just a space traveler, you're a time traveler. This is where the concept of time dilation comes into play. Time dilation, a consequence of Einstein's theory of relativity, dictates that the faster we move, the slower time seems to pass for us compared to someone stationary. In essence, time is no longer a fixed, unchanging entity. It's as flexible as a rubber band, stretching and contracting based on your speed. So let's take a look at the clock. From the perspective of observers on Earth, your round trip to Mars and back would take about 16 minutes and 40 seconds. But for you, the traveler, time would seem to pass differently. You'd look at your onboard clock and see that only 8 minutes and 20 seconds have passed. To you, it would feel as if you've made the journey in half the time it took as observed by the Earthlings. This is time dilation in action. It's as if you've stepped into a time machine, compressing what seems like a 16-minute journey into just over 8 minutes. Now, let's not forget about the return trip. The same rules apply. What seems like a 16-minute journey to the Earth observers would only feel like an 8-minute voyage to you. This thought experiment is a fascinating peek into the surreal world of high-speed travel and the strange effects it can have on our perception of time. Though we cannot travel at the speed of light, this hypothetical journey gives us a fascinating glimpse into the intriguing world of physics. So, what have we learned about traveling at the speed of light? It's a question that has intrigued us all, and today, we've delved into its intricacies. We've understood that the speed of light is a constant, unaffected by the observer's motion or direction. More intriguingly, we've come to see how the theory of relativity, proposed by Albert Einstein, changed our perception of time and space. We've also tackled the concept of mass-energy equivalence, learning that as an object approaches the speed of light, its mass increases. This leads to the paradoxical conclusion that to travel at light speed, an object would need infinite energy to propel its infinite mass, making such travel practically impossible. We've explored the fascinating phenomenon of time dilation. As we approach the speed of light, time slows down for us compared to those stationary. A journey to Mars and back, traveling at 90% of the speed of light, would seem twice as long to observers on Earth than to the travelers themselves. Yet, despite these revelations, the speed of light remains an unattainable frontier for physical travel. It is a limit set by the very laws of physics themselves, a speed limit for the universe. While we may not be able to journey at the speed of light, we can certainly keep exploring the mysteries of our universe, one thought experiment at a time.